In this video, I'm going to show you how to find the horizontal asymptotes of a rational function, like this one, where the polynomials in the numerator and denominator are of the same degree. The procedures we cover in this video will also help us figure out the horizontal asymptotes when the numerator and denominator aren't of the same degree. But to keep things simple as we learn the process, we're just going to consider the numerator and denominator having the same degree. So, to find the horizontal asymptote, we need to ask ourselves a question about the function. We need to ask ourselves the question, what happens to f of x as x becomes large? And by becoming large, we mean what happens when we plug in really big numbers for x. So big positive numbers or big negative numbers. Like, what does this function evaluate to roughly when we plug in 1,000,000 for x? Or what about negative 1,000,000? So in order to answer this question, we're going to take our function and we're going to rewrite it in an equivalent form where it's easier to see what happens to the function as x becomes large. So let's go ahead and write our function expression, 2x plus 1 over x minus 1. And now we're going to identify the leading order term in the denominator. So the term that has the highest degree. In this case, it's the x here. And we're going to rewrite our function expression dividing the numerator and the denominator by that leading order term, x. So divided by x on top and divided by x on bottom. And let's write what our fraction comes out to when we do that. So here we've got each term divided by x, so 2x divided by x, and then plus 1 divided by x, plus 1 over x. That's all from the numerator. And then on the denominator, a similar thing happens. So we've got x divided by x, and then we've also got negative 1 divided by x. So minus 1 divided by x. So now our next step is to simplify. So we see that we've got a 2x up here and an x on the bottom. The x's here can cancel out, x and x. Likewise, we've got a 1x on top here and an x on the bottom, so the x and x can cancel out. And we'll rewrite our function in simplified form. So we've just got 2 here, 2 plus 1 over x over 1 minus 1 over x. Now using this form, we're going to ask our question again. What happens to f of x as x becomes large? So looking at all these terms, what happens as x becomes large? Well, the 2 and 1 stay the same, but the 1 over x here and here, these both go to 0. And so let's talk about why that is. So as x becomes large, these terms both approach 0. And that's because suppose that we let x equal, let's just pick a decently large number, like 100. Actually, let's make that 1,000. And then, so if x is 1,000, then 1 over x becomes 1 over 1,000, which is equal to 0.001. Which is roughly equal to 0. If we picked an even larger number, the denominator would be even larger, the decimal would be even smaller, we'd be even closer to 0. Likewise, if we pick x equals negative 1,000, well, that's just 1 over negative 1,000, and that just tacks on a negative sign to what we had before, negative 0.001, which is roughly equal to 0. And if we made this number even more negative, like negative 1,000,000, then this denominator would just be an even greater magnitude, and this decimal would be an even smaller magnitude, so we'd still be even closer to 0. So this means that as x becomes large, this function expression takes on a value that's pretty close to just 2 plus 0, so 2, over 1 minus 0, so just 1, or just 2. So 2 here, that is our horizontal asymptote. Our horizontal asymptote is y equals 2. Here's another example. We still want to find the horizontal asymptote of the function. but this time we've got second degree polynomials on the top and the bottom. And the terms are a bit out of order. But the process is really still the same. We start out by finding the leading order term of the denominator. That just means the term with the highest degree. And that's this 4x squared term here. And in particular, we're going to ignore the coefficient. We're just going to focus on the x squared right here. So looking at that x squared, we're going to divide the top and the bottom by x squared. And that'll turn our function expression into an expression that's easier to tell what happens as x gets very, very large. So we divide the top and bottom by x squared, and our terms are each individually divided by x squared. So we've got 2x squared divided by x squared. And then we've also got our 3x divided by x squared. So plus 3x divided by x squared. And then on the denominator, all the terms individually are divided by x squared. So we've got 2 over x squared, then minus 2x over x squared, and then plus 4x squared over x squared. And then it remains to simplify. So let's go ahead and simplify this. So let's see, we've got an x squared, so these can cancel. We've got an x and an x squared here, so we can cancel the x and change this x squared into just x to the first power. And then 2 over x squared, that can't be simplified anymore. 2x over x squared, we can cancel that x, change this into x to the first power. And then x squared can cancel here. Alright, so let's write this in simplified form. So we've just got 2 plus 3 over x to the first, so just 2 plus 3 over x, all divided by 2 over x squared, then minus 2 over x, and then plus 4. Alright, so like we talked about in the previous example, these terms that are divided by x are going to go to 0. So 3 over x, that's going to go to 0, because as x gets really large, the denominator gets really large, and then 3 over a really large number is close to 0. And likewise, 2 over x is going to go to 0 for the same reason. And then 2 over x squared, well, when x is large, then x squared is even larger. So 2 over x squared is also going to go to 0, because that's 2 over an even larger denominator. So this will go to 0 also. And then we can simplify our expression. So this is just 2 plus 0, so 2. And then divided by 0 minus 0 plus 4, so just 4. So 2/4, or just 1/2. So 1/2 here is our horizontal asymptote. It's just y equals 1/2. As x gets really large, the function value gets closer and closer to 1/2. Here's the final example. We want to find the horizontal asymptote of a function which is a little bit more complicated than we've been dealing with, but the process is going to be the same. We still want to start off by finding the leading order term of the denominator, but in order to do that on this expression, we're going to have to simplify things a bit, because it's not very clear off the bat what the leading order term is. We're going to have to multiply things out. So let's go ahead and do that. We'll go ahead and multiply everything out, expand it out, so distribute this x squared and that x. So let's do that. So we get 1 minus, distribute the x squared to the 1, so 1 minus x squared, and then distribute the minus x squared to 3x, so minus 3x to the third. And then on the denominator, just distribute the x to both terms, so just x plus 4x to the third. Okay, now we can tell what the leading order term is. It's just that 4x to the third in the denominator. So we're going to focus on the x to the third part. Don't worry about the coefficient at all, just focus on the x to the third. and we're going to divide the top and the bottom by that leading order term, x to the third. Alright, so now let's go ahead and simplify. So we'll just divide each term individually by x to the third. So 1 divided by x to the third, and then minus x squared divided by x to the third, and then minus 3x to the third divided by x to the third. That does it for the numerator. And then in the denominator, we just have two terms here. So x divided by x to the third, and then plus 4x to the third divided by x to the third. Great, so now it's time to go ahead and simplify this monstrosity here. So x squared over x to the third, well, we can cancel out this x squared and then change the 3 to 3 minus 2, which is just 1. So this is just 1 over x to the first power. And then the x cubeds in the denominator and the numerator cancel here. So just 3. Then here we can cancel out this 1x and then change that 3 to a 2 because we're decreasing the power by 1. And then x to the thirds cancel here and here. So that just goes to 1 over x to the third, then minus 1 over x to the first, so just minus 1 over x, and then minus 3, and that's just 3. The x to the thirds canceled out, so just 3. In the denominator then, we have 1 over x squared, then plus 4. Alright, so now we can actually tell what happens when x gets large. Remember, when x gets large, anything that goes constant divided by x, that approaches 0. So 1 divided by x, as x gets very large, the denominator gets very large, and this is going to go to 0. By the same reasoning, 1 over x squared, that's going to be an even larger denominator than 1 over x, so this is also going to approach 0. And likewise, this 1 over x to the third, that's going to be an even larger denominator than 1 over x squared. So that is also going to approach 0. So now let's go ahead and simplify this. This is just 0 minus 3. So just minus 3 on top. And then 0 plus 4. So just 4 on the bottom. And that tells us what our horizontal asymptote is. Our horizontal asymptote is just y equals negative 3/4. As x becomes very large in the positive or negative direction, our horizontal asymptote is y equals negative 3/4. The function value approaches y equals negative 3/4. In all these examples, the numerator and the denominator had the same degree. But even when this isn't the case, we can still find the horizontal asymptote using the same process of finding the leading order term in the denominator and then dividing the numerator and denominator by it. We'll learn more about how that all works out in the future.